Thank you. Hello there, everybody, and welcome to this talk on decision-making in the absence of ground truth. I'm sorry I couldn't be with you live in Oslo. NDC, Oslo is one of my favourite conferences, but unfortunately with the way the turn that COVID took over the last few days, I wasn't able to attend. But anyway, I'm glad for the opportunity to present this remotely, and I hope you enjoy this talk. The way that I've got my setup working here, I can't actually see anything other than my presentation just now. So if anything kind of goes wrong, or anybody wants to ask a question or whatever, I'll be relying on the moderator to kind of interrupt me. So I'll just quickly go through the agenda for the rest of this talk. I'll give you a brief introduction of myself. We'll unpack the title a little bit because it might be a little bit confusing. We'll talk about how things work normally in a kind of data science project, or when you're asking a data science question that somebody in the business might have. We'll talk about defining the problem that we've got where we have the absence of ground truth. We'll talk about what is the path to success when you don't have any ground truth, but you still have to make business decisions, or as a data scientist, you still have to make predictions. And we'll talk about elicitation frameworks, and that'll probably be the majority of this talk. We'll talk about what an elicitation framework is. We'll talk about what we use it for. We'll give you a quick example. We'll give you an example of using one to elicit some of the information, the qualitative data that we need. Then we'll talk about how we project that qualitative data onto a quantitative distribution once we've got it. And then we'll talk about running our calculations as normal with that quantitative distribution. And then I'll take any questions at the end. I put questions here at the end because that's to fit somewhere in the agenda, but normally I like to take questions, if you do have them, as we're going along, because that way it's kind of fresh in your mind, and you can kind of ask the question when it's appropriate and actually on the part of the talk that we're actually at. So feel free to ask questions at any time, but there will be a slot at the end for questions. So quick introduction about myself. Really, the elevator pitch is that I'm the founder of a company called Darach AI, and what I do is I build cloud-based internet-scale analytics and AI modeling platforms, and I help businesses to build teams to operate them, and then I use the teams and the platforms itself to help the businesses predict the future. So let's unpack this title a little bit. Excuse me. I'm suffering from a bit of a cold at the moment, so forgive the coughing. So to unpack the title a little bit, this decision-making in the absence of ground truth, decision-making is quite straightforward. I mean, generally in terms of data science, we are doing predictive or prescriptive analytics. So predictive analytics is where we make a prediction about the future, and prescriptive analytics is that next step. So after we've made a prediction, we then say, and based on that prediction, this is what you should do. So that's the decision making part of it. The absence of ground truth is, what do we do when we have to make these kind of decisions, but actually we don't have any ground truth, i.e. we don't have any measurements. And we'll talk a bit about that later on. So that's basically what we're going to talk about. We're going to talk about how we do this decision making when we don't have any of the data that we would normally have. So with that, let me talk about how it normally works, how we would normally do data science. I've got something here which is a bit of a canonical example, really, in data science, and that is the kind of the Titanic data. So the Titanic data set, which is freely available. So how things would work normally is we'd read in some data from somewhere, and whether it be in a database, a data warehouse, or whatever. In this case, it's just a local CSV file. So what we do is we would read that data in. And then what we do is we have a quick look at it. So we have a look at that data. And for this particular example, we're going to do something really simple. What we're going to do is we are going to predict the probability of someone's survival based on their age and their sex. So the first thing we do is we have a look at that, and we can see the columns there. The first thing that we see when we've got an issue, excuse me, when we've got an issue, with predicting survivability based on age and sex, we can see there just from that column that we're looking down there that actually there are some missing values for age. So if we just have a look, the next thing we would do is we would just count them. How many missing values do we have? Well, we have 177 missing values, and since we need that, we need to do something about those missing values. So how we're going to solve that problem in this particular case is we would take the mean and would find out the standard deviation. So basically the mean of the ages and how spread out they are. Okay, and then what we would do is we would create a random age, which basically sits with the mean plus or minus the standard deviation. So that gives us a range, the minimum range being the mean minus the standard deviation, the maximum range being the mean plus the standard deviation. And then we create a random age to go in there. And then what we do is for every, in this part here, what we do for every missing piece of data is that we insert one of these random ages, which is in between that range. So once we've done that, we can just check again to see that we have no missing data. The next thing we look at, we want to use sex as it is defined here in the data set. We want to use that, but one of the problems that we've got is we can see, if we look at sex there, we can see it's defined as an object, and basically it's a string, and data scientists and data science in general like to work with numbers. So what we have to do is we have to fix that, really. And so what we're going to do is we are going to basically map where in the data set we have male as a string and female as a string. We're going to replace that with the number 1 and the number 0. Can I zoom in? That is a good question. Is that any better? Yep. That's as far as I can zoom in here, I think. Let me just check. I think that's as far as I can zoom in on this. Is it still quite hard to see? Okay, let me see if I can do something else here. If I can, let me come out of here. Yes, that's what is. Yeah, so if I just come in here, I might be able to scale that up a bit. I've lost control of my. There we go. That's it. Right. So let's go back now to here. Okay, so how's that looking now? Okay, excellent. So what we did was, as I said, what we did there is we basically mapped ones and zeros to the strings male and female. And then once we've read our data in, we've cleaned it up, the next thing we're going to do is we are going to grab our independent variable. So our independent variable is basically what we would measure in the real world. So in this particular case, what is the individual's age and what is the individual's sex? And then we grab the dependent variable, which is whether or not they survived. And it's called a dependent variable because it's dependent upon the passenger's age and sex. And then what we're going to do is we're going to fit those two values just into a logistic regression. Oh, lovely. Did I not run a particular one of these? Literally ran this afternoon and it worked perfectly. Okay, let me just run. I maybe ran a cell twice, which messed everything up. Just do that again. So that fixes age. That maps that. Yes, that's what I did. I must have ran that mapping cell twice. And now that we've got our logistical regression mapped, we can make a prediction as to based on the model that we've created. So basically, if we're going to predict that a 25-year-old male, what is the probability of them surviving the Titanic? So if we do that and we check according to our model, a male aged 25 has a 20% chance of survival. If we change that gender then to 0 for female, and we run that again, the female has a 74% chance of survival. And that just kind of reinforces this idea that we have about the Titanic. When it went down, it was a case of women and children first. And that just kind of reinforces it. Now, this is obviously a very simple, straightforward example. We would never ship a model as easy, as simple as this into production, but it gives you an idea of how things normally work. So we normally go through this process of loading the data, cleaning the data, building a model, and then making a prediction or a prescriptive, telling a business to make a prescriptive decision. That's how things normally work. Right, so if we go back to our, here, there we go, and just launch this. So that's how things normally work in the data science world. So let's define the problem. The problem we have is that what happens if we don't have any data? So here in the example that I gave you, you could see that we had, we'd have actual ground truth measurements. So we know who survived the Titanic and who didn't. But what happens when you don't have any data? Either the data doesn't exist, or it's siloed, or it's incomplete, or you just never stored that data. One of the things that I come across quite often as a data scientist is I'll be asked to solve a problem because management have decided that they want a new key performance indicator in order to help them make decisions going forward. However, that key performance indicator that they want will be based on data, or we need data to create a model that they just don't capture yet because management have only just thought of solving this problem. And so if you've not captured the data in the first place, there's going to be that time frame between when you actually want the answer to the question and being able to get enough data on board in order to be able to do the kind of traditional data science. Now, as data scientists, we can't just shrug our shoulders and say, well, you don't have the data, sorry, there's nothing I can do, and walk off. We still need to have an answer to that question. And so the problem here is, how do we go about answering these prescriptive and predictive questions if the data doesn't exist because we haven't captured it yet? So our path to success under these circumstances is we may not have the data, but what we absolutely will have in the organization is subject matter experts in that particular field. So the example that we're going to walk through, the hypothetical example that we're going to walk through this afternoon, is this idea of risk in some assets. So you're an organization, you have a number of assets, and you want to know what the actual risk is that you have in terms of monetary value from these assets failing. And let's say, for example, that you don't have that information. So you've never actually recorded what the failure rates are and things like that for your assets. So you say to yourself, well, I have no data for that. Well, that's not strictly true, because you must have subject matter experts in these assets. Somebody must build these assets for you. Somebody in your organization must maintain these assets. And just because you don't actually record the information from the things that they are doing doesn't mean to say that that data is not actually contained in their heads through years of experience. So where we don't have actual ground truth measured data, we can use the subject matter experts within your organization in order to elicit that data. And we'll talk about exactly how we do that in a minute. So what we're going to do is we're going to ask them basically their opinion. That's what we mean by qualitative data. So in that first box there, we're going to ask them their opinion. And then once we've got that opinion, we're going to map that to an actual numerical distribution. And then once we've got that numerical distribution, we can actually run our calculations just exactly the same way as we did in the previous example. So how do we use an elicitation framework? So we use an elicitation framework in this kind of following cycle, starting there at the kind of 2 o'clock position. We gather our experts together, and then we ask them some questions, and I'll talk to you a bit in a minute about what those questions are. But we ask them some questions to elicit an individual answer to those questions. And then as a group, we discuss where we have outliers. So if somebody says that their opinion is that a particular variable is going to lie around the 50% mark, for example, and you have a few people in the group, and some might have said that that value could be as low as 20% or it could be as high as 80%. So you've got some outliers there. And what you want to do is to have a kind of group discussion to kind of reach a consensus and bring those together. So you have that group discussion. And then you go on to do the elicitation in that kind of group way. So you kind of then agree on what the actual figure is. And then that agreement from the actual group as a whole, once you've discussed where your disagreements are and where the variances are and the reasons that some people might think some things vary more than you do, at some point you're going to reach that agreement. And from that agreement, we're going to create the data. So that's how the elicitation framework, or that's how, in general, elicitation frameworks operate. So there are a number of elicitation frameworks available, and the one that I tend to use most often is called SHELF, and that really stands for the Sheffield Elicitation Framework. And it's from Sheffield because it was Sheffield University, lecturers at Sheffield University who kind of came up with this elicitation framework. I use this one because it's probably one of the best known ones. It certainly has the most kind of academic merit behind it, and it's quite mature. You can see here from the slides that they're actually on version 4 just now. At this point in the presentation, I'm going to move to actually using their slide deck into mine for various reasons. One is copyright, and two is I don't want to misquote them on anything. So I'm actually using their slide deck here. So the first thing we want to do when we get our experts together and we get them in the room, on an individual basis, we're going to set plausible limits. And so what that means is, what we do is we ask them to write down their lower plausible limit for what we're going to call the quantity of interest. And in this particular case, when we're talking about risk is usually defined by the likelihood of an asset failing multiplied by the financial impact of that asset failing. So in this particular case, the hypothetical case, we're going to pretend that we don't know what the likelihood of an asset failing is, and we also don't necessarily know the impact of it failing throughout entirety of the business. So here, we'll just use one as an example. We'll use the likelihood. So what is this likelihood of this asset failing? And that's going to be our what they call their quantity of interest. So we're trying to elicit from our experts what the particular likelihood is of any asset failing, and we're going to refer to that number as X. So what we do is we come up with this lowest plausible limit that we can think of. We tell our experts that you should judge it to be extremely unlikely that, so if you could measure X, it would be extremely unlikely that X would be below that. Not actually impossible, but it would be extremely unlikely for the true value of X to lie below your chosen lower band. And then once you're happy that that is the case, then as an individual, you write down that number. And then what you want to do is you want to challenge that assumption. So you've come to that conclusion, but you want to challenge it. So what we do is we ask them to pretend that at some point in the future, we actually do measure that data. And the measurement comes out to be less than the lowest value that they thought it could be. And then we ask them, if we told them that, what would your reaction be? Would your reaction be that, yep, it's it's plausible for that to be the case and maybe I got it wrong? Or is your reaction more, it can't possibly be that low, the measuring system must be wrong, or the person telling me this must have got it wrong? And to challenge your value for L, your reaction should be B, okay? It should be, you should strongly suspect that an error has been made if it came back lower, than that. You want to do exactly the same thing then for the upper limit. So you get the plausible upper limit. Again, extremely unlikely that the true value of X lies above that value. You write that down. Again, you challenge your value in exactly the same way. And then what we've got now is you have your individual value, the plausible range for X. So we know that X, according to each individual expert, is going to lie somewhere between the number that they wrote down for L and the number that they wrote down for U. So it's based, they are subject matter experts, so it's based on their own experience and judgment, and there will be a little bit of variation between the experts on the panel. So we ask them to check one more time that they're happy with that, and then we move on. Having done that, what we ask them then to do is to come up with the median. So here what we do is we say, now that we have that range between the lower version and the upper version, we ask them to write down the median for our quantity of interest. And we're going to call our median the letter M. Again, we tell our individual experts that you should judge that it is equally likely that the true value of X is below M or above M. Whichever value that you select, it's equally likely to lie in either side. Obviously, M should be between the plausible limits, but resist the temptation just to plunk it down in the middle between the two, okay? Actually think about it and think, is it more likely to lie, is the true value actually the center, or is it more likely to lie towards the lower end or towards the upper end of our range? And how much more likely is it to be one side or the other? So some examples of what we're talking about here. Excuse me. So in this one, M is more likely to be closer. You have the range, but actually, the median being, so the median is defined as 50% of the data is going to be more than that, and 50% of the data points you measure is going to be less. And whereabout on the number line would that be? So basically, what we're saying is here on this one, the data which is higher than the median would be more spread out, and the data which is lower than the median will be closer together in its distribution, but still 50% lies between the lower and the median, and 50% lies between the median and the upper bound. Again, this is the opposite case where we actually think that the median, the true median, lies closer to the upper limit of what we think the range actually is. But again, regardless of where you put that median value, it's important that in your opinion as the expert, it is equally likely to be on the yellow side as it is to be on the purple side. Once you are certain that it is equal, whatever it is you put your median, once you're certain that it's equally likely for the true value of X to be on either side, then you can write down that value. Again, we want to challenge that. We don't just want to come to that conclusion and be happy with it, so we want to challenge with it. And the way that we challenge is the way we ask our experts to challenge this is if we say, well, let's suppose that you were offered a large prize if you can guess correctly where X is above or below M. Now, in this scenario, you won't lose anything if you guess wrongly, but you will get a large prize if you guess correctly. And then we say, well, which way would you guess? Would you actually guess the purple side or would you guess the yellow side? And if you have a preference, then you've got the median in the wrong place. If you're actually looking at this and saying, nope, actually, it would be impossible for me to tell the difference, then you've got it in the right place. But if you're thinking, oh, well, I would guess the purple side, then actually you've got your median in the wrong place and you should move it accordingly. So, and you keep kind of going around that cycle until you think to yourself, no, I couldn't, regardless of how big the prize is, I couldn't really make a judgment. It would just be a guess. There's no real reason. I don't have a preference for upper or lower. When you reach that state, then you've got your medians in the right place. Now we want to refine our median because this can be never really precise. So if you could increase your median just a little bit and still feel that it's equal likely to be above or below this new median, try to increase the value for M more until you reach a point where you think, no, I would definitely have to guess below. And at that point, you would kind of turn it a little bit, you tune it a little bit further down. Once you do that, your median should be in the middle of these 2 points. If your M value is much closer to one point than the other, you may wish to adjust it again. You keep going around that loop until you're happy. Once we have our range, our upper and our lower bounds, and we have our median, what we're then going to do is we're going to then add the quartiles. So quartile 1 and quartile 3. For the lower quartile, or quartile 1, as we call it, you're asked to write down your lower quartile for the quantity of interest. Again, it's X. And how we're going to do this is we're going to ask our subjects to judge that it's equally likely the true value of X is below quartile 1 or between quartile 1 and our median. So basically, we're doing the same thing as we did with the median, where we had our entire range. But what we're really doing here is we're trying to do that with the bottom half of the range. So we're going to use a very similar technique here. So quartile 1 should be between the lower value and the median, but it shouldn't necessarily be closer to one or the other unless you've got knowledge about that. So X is likely to be closer to M than to L if the values of X are only just plausible. So again, you're asked to make a judgment as to whereabout on that line it should lie. So here's some examples of placements of quartile 1. So in this one, you judge it more likely that quartile 1 lies closer to M than it does to L. Much more likely to be near M. What you should do is you should judge that it's equally likely to be in the light green. It says light green, but that actually looks a bit blue on my screen, which is a little bit confusing. But likely to be in the light green or blue, however you're seeing that, region. So it's below quartile 1 or in the dark green. And again, I'm seeing this as yellow on my screen, so I'm not entirely sure what's going on there. I don't know what you're seeing, but I'll assume that you can see the same thing as I can, but on my screen that looks yellow. So equally likely to be in that or in the yellow part. And once you've got that, you're going to write down that value for quartile 1. Again, we need to challenge our experts as we're going along. So again, we imagine there's a large prize for guessing whether it's above and below. Again, nothing to lose if you get it wrong, but plenty to win if you get it right. And then we ask you to consider, and if you have a preference, we ask you to move your quartile value based on that preference. And now we're going to do exactly the same thing for quartile 3, except it's on the other side of the median. So again, judge if it's equally likely to be one half or the other. Here's some examples. Again, it looks exactly the same. It's just the upper half of what we've seen before. So quartile 3 should lie somewhere between the median and the upper value. And you're asked to make a judgment as to whether it's bang in the middle, whether it's closer to the median or closer to the upper value. But regardless of where you place it, you should think that it's equally likely to be in any half, either the upper or the lower. And once you're happy that it is equally likely to be in either section, then you know you've got your quartile 3 measurement in the right place. Now, once we've done that, we do that as individuals, and then what we have to do is we go on and we use a system, or we use somebody, an imaginary person called the rational impartial observer. What we've got to do here is we say that different experts will have different opinions, and they'll have different opinions because they'll have been working for different lengths of time. People will be self-taught. Some people will have come from university. The university courses change over time. There's some more modern thinking. So your subject matter experts are likely to have a range of views. But what we have to do is, having elicited our individual judgments, what we have to do is to fit that to distribution, and we have to discuss our different opinions, trying to reach a common understanding. So we discuss where we have differences, we discuss why we have those differences, and why certain experts think one thing over another. What we're going to do then is we're going to try to reach a consensus or an agreement. However, what kind of consensus can we hope for? Because if you've ever worked, you know the old saying: if you take 3 software developers in a room, you've got 4 opinions at least. And what we're trying to do is we're trying to get a consensus with experts, and that's not necessarily easy to do very often. So you have to reassure people that they're not going to leave the workshop in complete agreement, and not being in complete agreement is totally fine. So there's no single answer to this question that we're going to come up with that's going to be right. And actually, even if we did come up with this with an actual answer, we still wouldn't know necessarily if it was right, because we're doing this elicitation method because we don't have the data. So we'd have nothing to test that again. But it's their opinions that matter. So there's no real starting point for asking for that kind of consensus. What we want to do is we want to discuss that, and we want to discuss why we think the things that we do, and why we've come to certain decisions. And then what we're going to do is we're going to have this hypothetical question called the rational impartial observer, and this hypothetical person is going to come to make the decision. So the rational impartial observer, how you imagine this person is someone who has listened to the discussions that you've had. So a bunch of individuals have come to the decisions, and then we've discussed where we don't agree. And this rational impartial observer, we kind of pretend that this person has listened and fully understands all of the arguments. The key thing is that this hypothetical person doesn't agree 100% with any one individual. So they're not siding with any one individual, and they don't have identical views to any person that's in the subject matter expert group. It's their own opinion is based only on what this observer has heard in the discussion. So what we ask ourselves is, we would ask the subject matter experts in that panel to consider the judgment that this hypothetical person might make. So what would it be? What would a reasonable conclusion for the impartial observer to think? We also acknowledge that the impartial observer may find some merit in all of the arguments or in none of them. But how would they weight? How would they add weight to each of them? And once we've done that, we come up with our kind of agreed conclusion. So by the end of this part, where we've done this group discussion, we then have this fixed idea of, we know what the lower bound is, we know what the upper bound is, so we have the range of our answer, and we're fairly certain that our answer lies somewhere within that range. We know where our median is, we know where our lower quartile is, and we know where our upper quartile is. And it's our subject matter experts that have come to that conclusion. Now, once we have that information, we can then go on to project that description onto. So what we have now is we have a qualitative description. So basically a bunch of subject matter experts have said, this is what I think the distribution, this is how I would describe the distribution. Well, with that information, we can go on to actually project that description onto an actual quantitative distribution. So if I just quickly jump back here to the examples, and here we're talking about generating. So here we're talking about generating the data. So if we go through this, what I've got here is I've got a function here called generate the data, and what it does is it takes the values that that were the output from the elicitation framework. So we have the lower bound here, we have our upper bound, we have our lower quartile, our upper quartile, and the median. And we ask actually, well, you know, how big do you want that kind of distribution to be? How big do you want how big a distribution, how big a sample do you want me to generate? So how we actually go through and calculate that is what we do. The first thing we do is we say, if the size that you've given isn't an odd number, then add one to it, because we want to be able to get that median, and we want to be able to have a correct median. And you can't have a median if you've got an even number, because the kind of definition of a median is that 50% of the data lies below it, 50% of the data lies above it. So you can't have a true median if you've got an even number of data points. And then what we do is we say, well, we know just from statistics and from maths that we know that 25% of the data has to be less than or equal to the lower bound and greater than or equal to quartile 1. So we're just going to generate some random numbers which fit in between that part of the description that our subject matter experts have given us. Then we go on to say, well, we know that another 25% of that data is got to be greater than or equal to quartile 1, but less than or equal to the actual median. And again, we generate some random numbers which fit in there. And then we say, lastly, that, or not lastly, but 25% of the data then has to lie between the median, so greater than or equal to the median, less than or equal to quartile 3. And then the final 25% of the data has to fit greater than quartile 3, but less than or equal to the upper bound. And once we've done that, we can generate our median just by injecting it into the list, and then we can sort it and we can return it. So if we go ahead and define that function, we can generate a distribution with I think it's 10,000 I put in there. So we can generate 10,000 data points based on a description of the distribution that our subject matter experts believe X would fall into. Having generated that, we can just go ahead then and test it to see that we did actually get the lower quartile and the median and the upper quartile that we had. So in this example here, we say that our subject matter experts have said, we don't think that the true value of X lies below 55. We don't think it lies greater than 100. We think our lower quartile 1 is at 66, and our quartile 3 is at 85, and the median lies at 75. So we generated 10,000. We generated 10,000 random data points or example data points, based on that description, and then we went back to check that our description does actually our distribution does actually match our description, and it does. So what I'm going to do here then is just to show you that there are a number of distributions that can come out of this. So if I basically create 6 examples and I basically generate some random data and then plot them for you, you can see that using this methodology and getting the descriptions, we can generate a whole bunch of distributions based on these differing descriptions. So we can basically get pretty much any distribution that you can imagine from these descriptions that we get. But this is an important part, because to do data science, we have to be able to work with data. And this is the part that actually maps the qualitative data, i.e. the opinions of our expert panel, to actual numbers that we will need to go forward. So this is how we actually take that qualitative opinion and we match it to actual mathematical numbers. So I won't bother starting the presentation again, because the next thing is to say, well, actually, now that we've done that, let's go ahead and run our risk calculation. So if we drop back here into our demonstrations, what I'm going to do now is I'm going to, as I say, in our hypothetical example, we are working for an organization. That organization has a number of assets. They are not entirely sure. They're not entirely sure what the risk is. At the minute, nobody's measuring that. They don't know what the risk is. They don't know what the failure rates are. They're not measuring it because up until this point they haven't had to. And then we're going to imagine that somebody from management wants a key performance indicator on how much financial risk that person has in the asset inventory that they have, or the assets that they use. So that's our hypothetical example. So what we're going to do is we're just going to quickly define a class, and this class is an asset. So we're going to assume that an asset belongs to a region. Regions are broken down into areas. Areas are broken down into sections, and each asset lives in a section, within an area, within a region. We take this, as we said before, risk is a calculation of the likelihood that an asset fails multiplied by the financial impact if that asset was to fail. And these are the things that we don't know, and so we've asked our independent expert panel to come up with a description of the likelihood. Again, lower upper quartile 1, quartile 3 median, and actually the impact. And then we have our risk as well. So what we're going to do is, in this next function will generate a whole bunch of assets for us, just basically test demonstration data. So what we do is we basically say we're going to have seven regions from 0 to 6. We're going to have 10 areas in each region, and we're going to have 20 sections in each area. Then what we're going to do is we're just going to create an asset. We'll give it a GUID as an ID, and we'll just call the region name with its index, and the same for area and the same for section. We'll just leave the likelihoods and these descriptions blank just now. We'll fill them in later with this part here, and then we'll append that to the list, and we'll return a list of test data. Then what we're going to do is we're basically going to generate some distributions for the likelihood and the impact. So we're going to generate some random descriptions. So these descriptions are the things that would come out of the subject matter expert panels. We're just going to randomly create a description as if the panel had happened. And so we are going to say that our upper and lower bound is between 100, between 0 and 100. We're going to say that the median is some random number between the two. That quartile 1 is a random number between the lower bound and the median, and that quartile 3 is a random number between the median and the upper bound. Having done that, we're going to then set those values into the likelihood description. And then we're going to do exactly the same thing for the financial impact. We're going to say the financial impact of any asset failure is somewhere between £10,000 and £500,000. And again, we're going to randomly set the median. We're going to set the median to be some random number between these two bounds, and again, exactly the same way. Quartile 1 to be a random integer between the lower bound and the median, and quartile 3 to be a random number between the median and the upper bound. And we're going to set that description into the impact, and then we're going to return that asset. And then we're going to generate that data based on that description. I'm not going to go over this function again because it's the exact same function that I went over in the last demonstration. But basically, this is the point where we take that qualitative description that our subject matter experts came up with, and then we create a real numerical distribution from it. So we'll just run that. And then what we can do is we can generate some test data along those lines. And then once we've got that test data, we can calculate the risk. So the risk is basically, how we're going to calculate this risk is we're going to say, our subject matter experts gave us this description, and we're going to create we're going to create a distribution with 100 data points in it that match that description for the likelihood. And then, given the description that our subject matter experts gave us for the impact, again, we are going to create 100 data points in a list, mimicking the actual data for an impact. And then what we're going to do is we're going to calculate that risk. We're going to set the risk to the asset to simply be the mean of the likelihood distribution here multiplied by the mean of the impact distribution here. And then we're going to return that asset. So we're going to calculate the risk, example risks for each item in our test data. And then once we've done that, at this point, we can treat it as if we have real data, as if we had measured data, as if we had ground truth data, even though that ground truth data never existed. So what we can do is we can do things like this, where we say, well, show me the top 10 riskiest assets that you have. And now all of a sudden, we have management information that we can actually show to management based on not just they are guesses, but they're educated guesses. This is a method for saying this is what your subject matter experts feel. So we have our top 10 assets here, and the value of the risk in financial terms that the company is carrying in order to have that risk within these assets. So we can do that, but what we can also do now is we can turn this list of asset objects we've got. We can turn that into an actual data frame, which is basically a table. So now you see we've got it in table form, so we can see the IDs, we can see the regions, we can see the areas, the sections, and the descriptions, and at the end we can see the risk. And then once we've done that, we can drill into this table. So you can imagine your visualization tool of choice, whether it's ClickView, whether it's Excel, whether it's Power BI, whatever. You can start drilling into that information now because we have it in table form. So here, I'm just going to repeat what I did there with the actual list of objects, but as a table form. And what I can do with that then is I can show the exact same. Breakdown by risk by region. But now that I have it in a table, I can start grouping then by other things. So I can say, well, actually, I want to group region and area, and I want you to tell me what my top 10 riskiest areas are. So here you can see now it says, well, actually, the area that has the most risk is actually region 0, area 6, followed by region 2, area 10. So we can start to produce all of this management information now. And again, we can go further because we said that actually this thing would then live in a section, and we can run exactly the same thing. So we can say, okay, we've drilled into the regions, we've drilled into the areas, but actually as a manager, I want to know where the risk is within the actual sections. And we can run the same thing again very, very quickly and very simply now. And we can say, well, actually, here are your top riskiest sections. So actually, as a section, it's section 11 within area 7 from region 5. And we can start then to do all kinds of data science. We can do all kinds of management reportings. We can make predictions. We can actually start to look then at making evidence-based maintenance choices. So previously, where we didn't have any ground truth or any data, what you probably find happens is the maintenance they carried out this year was the same as the maintenance they carried out last year. You know, in organizations where they have no evidence-based decision making, what tends to happen is we'll do what we did last year because it worked. We're not in big trouble this year, so what we did last year must have at least been somewhat successful. But now what we can actually do is we can say, well, actually, let's make some evidence-based decision making. And that becomes important when you do things like, well, actually, your maintenance budget has been reduced by 20% this year. We say, well, okay, if I've got 20% less money to do maintenance this year, where actually should I target that maintenance in order to get the largest amount of risk reduction for pounds spent? Okay, and to be able to do that, we have to be able to get data, and to get data where there's no ground truth, we use subject matter expertise, and we use subject matter expertise in the way that I've just described. So if I go back now, really, it's just back to questions now. So I don't really think I need to start the presentation and show that full screen. But basically, that's ran you through the actual principle that we have, where we don't have any ground truth, but as data scientists, we still have to make a decision. What can we do? We can't shrug our shoulders and walk away. And that is a methodology that you can use as subject matter experts within your own organization in order to come up with some mathematically justifiable numerical information that you can then go on to do data science and reporting on. So with that, and with like 8 minutes, I think we've got left now, I'll take any questions or comments from the room if you have any comments on that.
Hello, can you hear?
Everybody's like, no, I just want food and I want beer.
You can hear me now?
Yes, I can hear you now.
Or anyone wanting to?
Yes, please. Yeah, one small question before the beer. You're feeling the data, those, let's say, intervals between the quartiles with the uniform distributions. Is it justified, or is it does it actually make any assumptions on this hidden distribution? And could it be feasible to think about other distributions to fill this random data with?
So if I just pop back to here, to generating data, and we look at these distributions, see they're not normally distributed. So what you said there would be true if we had a lower and an upper bound, and we had a median exactly in the middle, and then the quartile 1 exactly in the middle between the lower bound and the median, and then quartile 3 exactly in the middle of median to upper bound. If that was the case, then you would get a somewhat normal distribution, or you could assume a normal distribution over that. But here in the elicitation framework, we specifically say, if you recall, we specifically say to the experts, don't just put it in the middle, right? Don't just go, okay, the median will be in the middle of the two things, and the lower quartile will be exactly in the middle between the lower bound and the median. We actually say, don't do that. And then once they've made the decision, we actually challenge them. We say, well, actually, do you think it's more likely to be in one or the other, and we get them to move that quartile and the medians around. And because you can have, and if you look back, if you recall the examples that I actually showed where medians and quartiles were towards or skewed towards one side or the other, that's actually what we encourage, because it's probably not the case that they'll be normally distributed. And you can see from these distributions on the screen that various random distributions that we create just by putting in random numbers there create distributions which are not normal. And we probably expect to see more of this kind of thing that I'm showing now than you would expect to see normal distributions. So to answer your question, yeah, absolutely. This works with different kind of distributions.
Anyone else? Okay.
Okay, are we done?
Yeah.
Okay, well, in that case then, thank you very much for listening. I hope you've learned something about elicitation frameworks, and you know what to do if you're ever asked to come up with a decision where there's no actual data. What to do as a data scientist when there's no actual data to work with. Thanks very much, and enjoy the rest of your conference.